Yeah, so last time, these are some of the things that we did. First of all, I talked about what a topological manifold is, right? So that's something, and yes, yeah. Hi.
Yesterday there was a question like S2, we cannot cover S2 by open set of R
Mm-hmm.
or something like that. I mean SN cannot be covered
By one chart,
one
right?
chart. Yeah, yeah.
Mm-hmm.
In RA or from
Yeah, that's right.
yeah.
Yeah.
So I mean, if so to prove that I suppose we can. So we have a map from SN to RN.
Mm-hmm.
Hello.
Yeah.
Now we subtract a point from SN. So we
Yeah.
subtract the corresponding point from RN.
No, see, I mean, if you have so it's not just any map, right? So it needs to be a
SN is compact.
homeomorphism. Yeah, exactly. So it will be a compact. So SN is compact, and so an open set in Rn is never compact. So you can't have something which is homeomorphic to SN.
I see.
That's all. That's all. Yeah, it's just it's a kind of it's a minor, point set topology fact. Okay, but we can cover it with two sets, two charts. Yeah. Okay. Yeah, that's right. Okay, so yeah, that was an example of a topological manifold. So, but let me just quickly remind you the kind of the things that sort of this definition. So it's three things, right? Hausdorff, second countable, the Hausdorff, second countable, and we'll see why second countable is useful today. And it's locally Euclidean, and that's the most important thing, right? So that's the topological manifold, and then we saw the definition of a smooth manifold or a differentiable manifold, and this is the way I defined it. It's a smooth structure on a topological manifold, and by smooth structure I mean you take an atlas, a smooth atlas, and smooth atlas is just a collection of charts as before, but they are compatible, right? So the charts, they differ by diffeomorphisms on their overlap. Okay, so this is the notion of a smooth manifold, and we saw some basic examples. Well, the basic examples that I mentioned was basically sort of the kind of the non-trivial ones, at least, with spheres and real projective spaces, and I also mentioned you can take products of them. Well, maybe S1 cross S2 is an example, and so on. So there are plenty of examples, and later on, of course, we'll come across more examples, like the Lie groups, which we haven't yet come to. That's sort of part of the course title, and that'll provide a large class of other examples as well. Okay, and the reason why these are smooth manifolds is something I left for you to check. I had described what the charts are that makes them manifolds, topological manifolds, and then you can sit down and check that the charts I provided on SN, on RPN, they differ on their overlaps by smooth transition maps. Okay, so that's the set of examples that we got. Maybe I should just kind of align it better with this basic examples, and then, oops, and then along the way we saw some. I mean, we talked about the notion of a smooth function, right? So this is what a smooth atlas is useful for. You can define what a smooth function on a smooth manifold is, and you can also talk of smooth maps between two manifolds. So if you have M and N, sort of two smooth manifolds or differentiable manifolds, so then you can talk of a smooth map from M to N. And the reason why you can do that is because locally at the level of charts, you can talk of a smooth map between subsets of Rn, between open subsets of Rn, and that makes sense. That is fine. And so via those charts, you can define what smooth map between manifolds is. Okay, so just to recall, some of you, I think one of you at least asked about this. So we don't. So there's another notion that we saw was the notion of a diffeomorphism. So let me just remind you about that. So use blue. So another thing is also a diffeomorphism is a special smooth map between two manifolds, which is this is it's a homeomorphism. You can think of it as the way I defined it, it's a bijection. But it also so such that F and F inverse are smooth, right? Yeah, so it's kind of I mean, it's an exercise to see that it also implies that F is a homeomorphism. It's sort of as being a diffeomorphism is stronger, right? Because just like, you know, sort of something being smooth is sort of stronger than requirement is stronger than having just requiring continuous. Okay, so this is a diffeomorphism, and so ultimately we'd be interested in smooth manifolds up to diffeomorphism, right? So the example that I asked you to work out was you know, sort of this is where, you know, you take R and you have two different smooth structures, right, that you define by an atlas, a single atlas covering the whole of R, and so there's a diffeomorphism between them. So they are really the same smooth manifold. Okay, although the atlases we gave on these two define two different smooth structures. So these are sort of we saw there were two different smooth structures, but they're not really different smooth they don't really define different smooth manifolds because there's a diffeomorphism between them. Okay, and sort of this is just you know, because you know, you have freedom in choosing an atlas, right? So sort of you can it's sort of the maps in a particular, so the atlas that you've chosen, you know, you can choose an atlas in different ways, and you know, they need not always be sort of compatible with you know, sort of one another. These different atlases need not be compatible, but as long as, you know, so if you have the same underlying smooth manifold, I mean, it's really the same space that you're talking about. So this is what's going on. I mean, for instance, I mean, if you have let's see, so if you have a topological manifold M, so let's say this is a topological manifold, and you have a smooth manifold N, and you have a homeomorphism from one to the other. So this is a homeomorphism. Then you can so if you have this kind of setup, so then you can define then so M also becomes a smooth manifold, right? So the M is a smooth manifold also, right? And this is you can define charts on M, which are, you can define a smooth atlas on M by kind of pulling back the smooth structure on N. Okay, and so the way that it works is you have M, you have N, right? And so you know that so if you take well, if you take a, so if you take a chart here, so N is a smooth manifold, and you have a bunch of charts that differ nicely on their overlaps, right? So these are some, maybe some, both are N dimensional, let's say. Otherwise, you can't be homeomorphic. If they're homeomorphic, they have to be the same dimension. That follows from the invariance of domain. But in any case, so you have these charts on N, and you have this homeomorphism F. And the thing about a homeomorphism is that there's an inverse, right? And F inverse. And so so these open sets, let's call them U and V, they go to some open sets U prime and V prime, right? And so you can define a chart on M by taking U prime and the map of F composed with V, right? So that's going to be some sort of a chart defined on M, and similarly you can define a chart for V is psi composed with F, and so on. So you can just compose your charts over here on this side to going to open sets in Rn by precomposing with this map F. And then, so this compositions that you get are still going to now define, sort of these charts, this time on open sets on M, right? And so, and these are going to be compatible because here, so the transition maps remain the same, right? So you're still defining the same transition maps. And so this gives you a smooth atlas on M. Okay, so so you're using the smooth atlas on N and so pulling it back. This is called a pullback of the smooth structure. So you're pulling it back to define a smooth atlas on N. So so if you have this kind of setup, then it's M and N are really the same manifold again, because F is a diffeomorphism. So by definition, you can sort of if this pullback, so M is diffeomorphic. So I'm going to often use this notation to say diffeomorphism. This is the equivalence in this category of smooth manifolds. So this is a diffeomorphism. So so let me just maybe I'll add this as a remark here. So I'll just put it here. So and so also and M and N are diffeomorphic. Okay, so they were homeomorphic to begin with as a topological manifold, but now if you define the smooth structure by pulling back, then it's easy to check that this is M and N are going to be diffeomorphic. So this is one example in which these definitions sort of work together, and so this is one example where your manifolds might maybe look different, but as long as they are diffeomorphic, they would have the they would really be the same smooth manifold. Okay, so anyway, so maybe I'll
hello,
have,
sir.
Yes. Hi.
Sir, in this entire construction, where did we use the fact that M is locally Euclidean?
Well, I mean, we used the fact that yeah, so we use the fact that we didn't use the fact that M is locally Euclidean, but use the fact that M and N are homeomorphic, right?
So we can just work with any topological space M, right, which is homeomorphic to N, and then we can pull the smooth structure on N to M.
Yeah, that's right.
Yeah,
of course. Yeah, but if it is something is homeomorphic to a topological manifold, it is also automatically a topological manifold. That's so it's sort of
okay. Yeah. And one more question is the way we define the smooth map. So while defining a smooth map, do we assume continuity of the map, or I don't think it can be proved from the definition, right?
That's a good question. Well, yeah, it can. I think it can be. I mean,
I mean, the pre-composition and the post-composition are homeomorphism. So if you just...
Yeah, that's right. Yeah, so the way that we've set it up, so all this depends on how you define. So different books would have different ways to define, what a smooth manifold is, etc. The way we've set it up, we kind of already know that these charts. So maybe I didn't give this a name. So this chart is psi, right? So these charts phi and psi are homeomorphisms. These are homeomorphisms, right? Yeah, so if you have a map between two manifolds, let's say, and so then so locally you're always going to be a continuous map, because so if you're smooth, so because I mean just because, yeah, so if you're right, so let's see what was the local picture. So maybe I've sort of run out of space here, but so let me try to make myself some space here. So if you have sort of M and N, and you have some sort of the level of charts, remember, is from X to F of X. You want to look at a neighborhood of X on M and neighborhood of F of X and N, and at the level of charts, you have this map, right? So let's call this phi and psi, and so you have psi composed with F composed. And so we know that these two are homeomorphisms, and this is a diffeomorphism. Sorry, I mean, this is a smooth map. I'm talking about smooth maps, not necessarily diffeomorphisms. But so we know that this is a smooth map, and these are homeomorphisms. So a smooth map between subsets of Rn is automatically continuous. This is something you are familiar with. Okay. So this is, so now you have a, so if you look at F now, it's a composition. This F is now a composition of all continuous maps. So this. I mean, this diagram commutes, right? So it's a composition of this, and psi inverse. And so this is a composition of continuous, hence it's
okay, I understand.
So it's automatic from, yeah, so it's automatic from our definition. But yeah, keep in mind that certain other definitions, if you come across other books, they might be requiring that F is continuous, and that's because they might have defined this phi and psi to be just bijections, for instance, right? Things like that. So yeah, anyway, so the way that I've set it up, I think it's, you just need smooth at the level of charts. Okay. All right. So are there any questions about the stuff? Yes.
So here we've taken F to be a homeomorphism, but to begin with, we are not saying that it is a smooth map.
Right.
So if we do this, then will we get something like a square and a circle are homeomorphic? So if we take the circle as a smooth manifold, then that means the square is also a smooth manifold. Will we get something like that?
Yeah, absolutely. Yes, exactly. That's one of the things that you get. Yeah. So if you, so a square is homeomorphic to a circle, right? So you can pull back the smooth structure on the circle and define a smooth structure on the square. Okay. And so the square, although if the way that it sits in R2, you know, the induced thing seems like it has corners, etc., but that's just from the way that it's sitting inside R2. But as an intrinsic manifold, it can be given a smooth structure. Just
okay.
like
So the smooth structure that we are giving through a homeomorphism to a circle is different from the structure that is induced by it sitting in R2. Is that right?
Yeah, there is no smooth structure coming from the, you know, sitting inside R2, because yeah, I mean, yeah, it's not sitting in a nice, you know, smooth manner. Right? It's not a smooth submanifold of R2. Okay, we'll talk about these notions very soon. So there's a notion of being a submanifold, where you have a bigger manifold, and then you have a submanifold is some other smooth manifold sitting inside it. So a square is not going to be a smooth submanifold of R2, but it is some manifold, and it's smooth manifold in its own right. Okay, so
yes,
yeah, so that's right. That's right. Yeah. Yeah, that's kind of a distinction. Okay, okay. Any other questions? Somebody else had something to ask. Okay, anyway, yeah, so, right. So the first topic for today is sort of, now let's sort of move on from the definitions. So,
Sir, one question small.
yes, yeah,
so
sure.
it's like, is it something related to inner products? Because circle is like L2 and square is like something else, I mean, L1, I guess.
Well, not quite. No, I mean, yeah, so it is true that the square is the unit, ball in L1 norm in R2, but that's I think a separate fact. It is not really related to this
Okay.
note I'm talking about. Yeah. Okay. All right. So yeah, by the way, you folks can also look at the various, the books that I had listed. I'm sure there are more. I mean, it's just my ignorance of, the other books, but whatever books you like, and look at how they define things and how they discuss. I mean, there's one of the books is, Lee's book, LEE, Lee's book on smooth manifolds, and you can have a look at the discussion about all these things there as well. Okay, and that might supplement some of the things. I might answer some of your questions or doubts or something you might have. Okay, but feel free to ask me as well, and you can send me an email or something. All right. Okay, but moving on. So one of the first things I want to tell you about, from after these definitions, is the existence of partition of unity, and you will see that. This is something that sort of needs the second countability assumption in the definition of a manifold. This is something actually, so one can talk about partitions of unity, etc., on even topological manifolds. We'll be assuming we have a smooth manifold at our disposal, but in any case, this is a completely topological thing where second countability is used. So what's a partition of unity? This is a very useful tool that comes up often when you deal with smooth manifolds, and we'll see various applications of it as we go along. So so the partition of unity is always subordinate to an open cover. So let me just write the word subordinate to this. So you start with an open cover of M. So open cover, as you might recall, is a collection of open sets that cover M. That the union is the whole of N, and then a partition of unity subordinate to this cover is a collection of functions. Okay, so it's a collection. Maybe I'll just say it's a countable collection of functions. When I talk of smooth manifolds, are really these are actually smooth functions. So maybe I'll write smooth bracket. Smooth functions. Let's call it phi I. And since it's countable, I'll index them with natural numbers such that, first of all, so these phi i's are non-negative. So let me let me sort of recall that. So the phi i's are now sort of functions on M. Okay, so M to R. And so phi I, so is non-negative means, so the way I've written it here, it just means that for every x in M, right, this value of the function phi I of x is greater than or equal to 0, right? So that's so it's non-negative. These functions are non-negative, and the second property is that the support of phi I, I'll just denote by sup phi I, is contained in an open set in the cover. Some open set belonging to this collection of U alpha. Okay, I guess so a priori this open cover need not be countable, but we'll see that we can always, since we are dealing with a second countable space, we can always refine it, get another open cover which is countable and which so that each open set is contained inside one of these U alphas. Okay, so these are the supports are kind of sitting inside. So every support of a function means the part where it might be non-zero, right? So outside a support, a function is zero. So all of these phi i's are actually basically living in, that takes non-zero values only in some open set, or some set contained in one of these open sets. Okay, this is what the support, the second condition means. And then the third one, this is again the defining property of a partition of unity, is that if you add up these phi i's at every point x, the sum makes sense and it is equal to 1 for all x and n. Okay, so if you add up these functions, you get 1. So that's why it's called a partition of unity. You're dividing the constant function 1 into these bunch of other functions. Okay, each one of them is supported on a small part, namely something contained in U alpha. Okay, now to do all this, I need to, sort of, even for this to make sense, even for this sum to make sense, I need to, make sure that only finitely many terms. This seems like an infinite sum, but I want really that only finitely many terms are non-zero. So this actually turns out to be a finite sum. Okay, so maybe I'll mention this here. So sort of this in our construction, after this construction, this will turn out to be a finite sum. So most of these, all except finitely many, would be actually be zeros, so that this sum makes sense. Okay. All right. So that's a partition of unity, and so the basic fact is that such things exist. So let me tell you why it does. So this is a collection. Yes.
Are you assuming this collection to be locally finite or something like that? Or why is the sum be finite?
Yeah, so as I said, this will turn out to be a finite sum. So at the moment, we are not assuming that locally, that U alpha is locally finite, but yes, you're right that, ultimately we'll be replacing this open cover U alpha with some open cover which is locally finite, and work with that instead. And so then it will turn out, that's why I said it will turn out that this is, the way that we'll define these phi i's, that this sum will be finite. So then this makes sense. Okay, this whole thing, this is not really an infinite sum. This is going to be actually a finite sum. Okay, right? So yeah. Okay, so all right. So how do you prove this? Well, first of all, let me sort of take a step back and talk about existence of smooth functions on M. I mean, so this is a partition of unity is a special collection of smooth functions, sort of related to this open cover. But you can ask, okay, so how about smooth functions in this first place? Well, so there are. I mean, so first I want to convince you that there are lots of smooth functions on any smooth manifold, and here's one way to construct them. So the one way to construct them is to consider what is called a bump function. Okay, so let me start with this. Well, let me call it a lemma, but it's really a sort of a basic thing that. So let me call it a bump function. This is what is called a bump function. So this is a non-negative smooth function phi. Well, let me go to the next one. Phi from Rn. So I'll define it on Rn. So Rn to R, that equals 1 on, let's say, a unit cube. so it's a product of, so this is all these intervals on these various coordinate axes, and equals 0 on the complement of a larger cube on, let me just say, on 0 on, so -2, comma 2, -2, 2 whole complement. Okay, this is again sort of n times. So it's like, so if you R2, you know, so you can sort of imagine that, so these are the two axes, and so it's sort of, this is the, let's say, the unit cube, and then you have a bigger cube, 2, this is size 1, and so it's going to be 1 in that green region, and then it's going to be sort of 0 outside here. In between is sort of smoothly interpolating between 0 and 1. Okay, so that's what this bump function would do. Okay, and there are, I mean, various ways to construct bump functions, but let me sort of just briefly sketch such a thing. You might have already seen such things already, but let me just tell you. So you can go step by step. You can first do things in dimension 1. Okay, so you can define a single variable function, a smooth function, which vanishes if you are, if this is where t is this variable, single variable, and vanishes whenever t is less than or equal to 0. Okay, so oops. All right, and then so this is the way that you define it, and so the graph of such a function would be 0 till 0, and then it will slowly increase, and you can check that it is smooth. I mean, it's at t equal to 0. So this is the point where t equals 0. So if you compute all the derivatives, they'll all be 0, and so it's sort of smoothly going from the constant function to something which is non-zero. On the right, for t positive, it is this the function values are all positive. Okay, and from this, this is not quite supported on an interval, but if you can easily, so you can define a new function which a couple of steps. First of all, you can define g of t to be f of t divided by f of t plus f of 1 minus t, and that, if you think about it, the graph of that will be something like this. It'll kind of be 0 for a while, and then it'll smoothly jump up to be a constant after. So this is like a step function in some sense, but smoothened out. So between 0 and 1, it kind of goes from being constant 0 to being constant 1. Okay, and this is easy to check that, you know, if you define it. The fact that it's smooth is also easy from the very definition. Since f is smooth, the gt, if you define it like this, it will be smooth. And then finally, so if you take, if you define h of t to be g of t plus 2 times g of 2 minus t, then it is something which will be 1 in this interval -1 to 1, and it will be 0 outside -2, 2. Okay, so -2, 2. So this will be like a bump function. This is how a bump function is constructed in one dimension, and then you can just you know, for every coordinate axis, you can define this function, and so you can take the product, and this will define the bump function in n variables. So this will be something like h of x1 times h of x2, h of xn, where h is this function that we just defined, because this depends only on single variable. Okay, and so this is something defined in Rn to R. Okay, and so this is going to be so the support of this is this green part, which is somehow is sort of contained. So this green part here is where, so sorry, the support is, in the green part it is constant 1, but the support is contained in this, in this the square here, this larger square, right? Because outside it is 0, right? So this orange portion is 0. So in particular, the support would be sort of contained in, let's say, if you take some sort of ball of radius 3 or something like that. So this contains the support of this kind of function. So these can be used as a building block for our construction of a partition of unity as well. But let me sort of just tell you the corollary that we were after. Well, it immediately see that any smooth manifold M admits lots of smooth functions. And why is this? Well, you can just make a function live on one of the coordinate charts. So remember that the smooth manifold M has, so you can pick a coordinate u, and you have a phi, and maybe you have something. So this maps to some open set in Rn, right? So this is some open set. So phi of u is some open set in Rn. But you can always sort of, by a sort of diffeomorphism, you can make it lie inside inside some ball of radius 3 or something if you want. But in any case, the idea would be to just define a bump function which is supported inside phi of u. So maybe let me, the way that I'll do it, I'll just so let's imagine that that you can fit a ball of radius 3. So this is some ball centered at some point, let's call it y, of radius 3. Okay, so you can always arrange that, right? If your phi of u is very tiny, you can always sort of dilate it, and so that's going to be a homeomorphism of Rn anyway. So you can just kind of sort of just expand and then make it big. Okay, so and so you can fit in a ball of radius 3, and you can define one of these bump functions, one of these phis that we constructed on this this ball of radius 3. Well, actually, the support would be contained in a much smaller sort of cube, but a cube of side length 2. But nevertheless, that cube would be sitting inside this region, and so you can define this bump function phi over here. Oops, maybe I shouldn't have called this phi as well. Let me call this b, just because it's a bump function. Okay, so this is the bump function from the lemma. Okay, and you can define everywhere else. So everywhere else you define it to be 0. So on u, you can define your function to be composed with phi. Okay, so this guy here, and everywhere else you define it to be 0. Everywhere, even sort of the part of u which is the pre-image of the complement of this ball of radius 3. So maybe that's part of u, but you define it to be 0 there and 0 everywhere else. Okay, so this is one way that the bump function really just lives on one of the charts. Okay, so you're thinking of one of the charts as a part of Rn, and then you are just applying the bump function there. Okay, and everywhere else it's 0. So this is one way that you can construct lots of smooth functions, right? So you can do it for any chart and so on. All right. Yes, I see a hand up. Yeah.
So, do our definitions require that the support of a function is a closed set?
Well, a support is by definition a closed set, right? Because it's the
Closure of yes.
yeah. So support would automatically be closed, right? So yeah.
Just wanted to confirm it because I saw some alternate definitions in some places.
No, I think yeah. I mean, support is
Closure of
wherever.
the function of all points of the function is not zero.
Well, yeah. I guess. Yeah, for us, I mean, it probably doesn't matter, but yeah. So you can think of it as you can take the closure if you want. That's okay. Yeah, yeah. I mean, probably doesn't matter. Even if it's an open set, it's okay. Okay, it's a set of points where it is not zero, right? I mean. Or sorry, no, it's not even that. It's the complement of the set of points where it is zero. So maybe if you think of it that way, then it's actually by definition an open set, right? So
Yes.
yeah, so yeah, maybe it's better to keep it in as an open set. Yeah, because so it's yeah, maybe it doesn't matter at the moment. Okay, so
I think it's so that we if we have some function that has some roots at some like a polynomial function with roots at 2 points or something, then we can say it's supported in the whole manifold instead of saying that it's supported at the manifold minus those 2 points. I think for that reason, closure is included in the definition.
yeah, you might be right. Yes, that makes sense. Yeah. So maybe it's better to take the closure instead. Yeah, that's right. Yeah, but in our cases, the support would be something which is always, we're going to enclose it in a larger ball. Okay, and a ball, ball, even if we take it open, you can always take a closure of it and then it'll become a closed ball. Okay,
Yes.
so the Euclidean space has that advantage, and since manifolds are locally Euclidean, there is this advantage that if you talk of an open ball, you can easily talk of closed balls because we can just take its closure. Okay, so yeah, okay, yeah, thanks. Yeah, that was it's good to clarify. Yeah, so okay, so then in that case, if you want, you can always think of these supports as closed sets. Okay, all right. So okay, so now that we know that it has a lot of smooth functions, basically functions you can always construct that lives on one of these charts. What's the idea of constructing a partition of unity? Well, so the idea is quite simple. You just construct a bunch of bump functions. So let me tell you the idea, and then so we'll see that we'll run into this problem of making the sum finite, which is what one of you also raised. So the idea is very simple. So you construct oops, I do the wrong green. Construct, maybe I'll use blue. A bump function supported, let's call it Fi, supported on I should call it Bi. Supported on each open set in the open cover, and then define phi I. This is the partition of unity that we are after, so at every point, so these the BIs are all, these are functions defined on M, but although they are supported inside one of these open sets in the open cover, and you can define phi i's to be BI divided by the sum of all BIs. Okay. All right, and so if you define it this way, then if this is well defined, this is just the idea. I'm not saying that, so the many there's several catches here where you have to make things work. But if you can define it this way, then it's clear that that these sum of phi i's will be 1. Right. So all you basically need to do is to make this work. But here you run into some issues here. First of all, when I say BI, it's kind of implicitly assuming that we have an index set that is the natural numbers, right? So this I runs from, sort of, let's say 1 to 1, 2, 3, and so on. And the other problem is that the sum, how do you make the sense of the sum if it is infinite? So you want to make this finite. So we kind of need this a little bit to make this argument work. We need, so this I've already written this here. The open cover that we started with has a, let me also add the word countable locally finite refinement. And what this means is that, remember, we had started with this cover U alpha, where this index set could be uncountable, could be a large number of open sets here, but you can sort of, the idea is that you can sort of replace it. Okay, so instead of this, you replace this, so replace with some other cover. Let me call it V alpha, but so let me call it VI now. Actually, let me just stick with U's. Okay, so I'm going to call them UIs, where I is now some countable collection, so it's sort of a countable index set. So UIs is countable collection, and so that's the first word, countable, here. And it's also locally finite, which means that every point in the manifold belongs to only finitely many of these UIs. Okay, so this locally finite would mean that sort of each X and M belongs to finitely many UIs. Okay, so so this would take care of this sum being finite. Okay, because if you have locally finite, then for every X, so your BI of X would be, remember, BI of X, the support of this is in one of these open sets. Okay, if UIs, so outside that it's 0. So if X belongs to only finitely many of these UIs, then X is outside everything else, and then so the sum would only have finitely many non-zero terms, and then this makes sense. Okay, so and refinement just means that these UIs are contained in the original U alphas, right? So refinement would mean that so each UI is smaller. It's a smaller thing. It's contained in U alpha for some alpha. So this is each U alpha, alpha to I. Okay, so this so you're kind of refining an open cover means you're finding something with smaller open sets. Okay, so this is a lemma, the fact that so this can be done, and this is where the second countability plays a role, as you can sort of imagine. So lemma is that every open cover of M has such a refinement, so a countable, locally finite refinement. Okay, and this okay. So let me tell you about the proof of this. So the way that the proof the works is that you use the second countability. So let me first sort of use a sort of a warm-up lemma. So the warm-up lemma that every open cover has a countable refinement where each open set is pre-compact, means that its closure is compact. So each open cover of M. Remember, now we are always in a smooth manifold. This works even for a topological manifold. Okay, so the thing about so the way that pre-compact works is here we use this property of Euclidean space that we just mentioned. The fact that if you take an open ball, its closure is compact, right? So pre-compact means that the sort of the closure is compact. This is true for open balls in Euclidean space. Okay, so true for open balls in Rn. And you can use that in the following way. So if you, well, first of all, what can you do? So if you can first get some, you can first get a where each open set is pre-compact, but just that's very easy. So every sort of U alpha, you can pick the collection of balls. You can sort of for every point there is a ball that is contained inside U alpha. Okay, so that's going to give you a refinement, and so every point, but you're adding lots of balls now. So every point there is a ball, but in any case, all these balls would be pre-compact. So it's easy to get a refinement where all the open sets are pre-compact, and then you can make it countable also because your space is second countable, right? So your manifold M is a topological space which is second countable. So each of these so what can you do? So well, you can choose so you can choose, first of all, you can make sure that your countable basis is pre-compact just by using a similar sort of replacing points by open balls, and you can when you pick these open sets, these balls, we can pick elements of the basis of that countable set that these are contained. You can restrict your choice of these balls to elements of that countable basis. Okay, so maybe let me, in the interest of time, since I'm sort of running out, let me not skip the details of this. This is kind of an exercise on second countability. So this is exercise sort of this uses second countability. Okay, so you can just sort of make, so it uses second countability and this fact that I said that open balls are pre-compact in Rn. Okay, so the first step, you might want to refine your, first of all, you might want to replace your countable basis with things which are pre-compact. So you had a countable basis of open sets which are all pre-compact, so you can do that. And at the second stage, so when you for every one of these open sets in the open cover, you can just sort of kind of replace that with a collection of open sets which belong to that countable basis, and all along you're kind of only using countably many open sets because your own basis is countable. Okay, so in any case, this is something that's sort of just some point set topology, and you can easily do that. All right, and once you have something which is a countable, open cover by pre-compact sets, it's easy to do the following, it's easy to produce a compact exhaustion. And what is a compact exhaustion? Well, it's a sequence of open sets. Let's call it GIs. And since it's a sequence, it's sort of a countable sequence. And these are all sort of in the manifold, of course, such that the closures are compact. So these are all pre-compact, as I sort of want. And then these closures, GI closures contained in the next open set. So it's like it's getting bigger and bigger, and it exhausts the manifold. And sort of the M is the union of all these GIs. Okay, so it's sort of the sort of picture keep in mind is maybe G1 is here, G2 is there, and sort of getting bigger and bigger, and sort of GI and so on. Okay, and it fills up the whole manifold. And so so how do you show this? Well, this is also easy once you have a countable basis of open sets with compact closures, because you can take GI to be so let's say G1 to be one of these. So maybe I'll end with this warm-up lemma. We've run out of time, but so let ui from I to infinity be a countable basis of open sets with compact closures, and then you can let me put this down, compact closures, and then you can sort of define the GIs as follows. The G1 is U1, and we'll define so the GKs. So each GIs would be actually the union of some number of these elements of this countable basis. So it will be some collection of up to, let's say, some, I don't know, some UJI. Okay, so and so how do you define this? So we shall define each of these to be this. Well, you define this so that the GK, the GI closure. So how do you define this GIs? Well, you define this GIs. Let me actually sort of call these Ks. Okay, so we let J of one is 1, right? So it's a J of 1 is 1, and you define the next J by looking at the smallest integer bigger than JK, so that the GK closure is contained in finitely many this union. Okay, so remember that closed compact. So this is compact. Okay, so so U1 closure is compact. So this will be contained in. It will be covered by finitely many of these open sets, and so you pick the index so that it is contained in this union. Okay, and so you can define, once you have that index, you can define G of K plus 1 as this union that appears on this right-hand side. So J of K plus 1 UIs. Okay, so this right-hand side is going to be our GK plus 1. And so this way, so inductively, you can construct the sequence, and it's going to get bigger and bigger like this. Okay, and so from these two warm-up lemmas, it's actually easy to prove the original lemma that of having a locally finite refinement, and maybe we'll start with that the next time, and then that's all I'll say about the existence of the partition of unity. So I've run out of time, so I will not finish this.
Sir, is it clear that GK plus 1 closure is compact? I mean,
yeah, because sort of each of these UIs have compact closure, right? And then and it's a finite union, so it's going to be contained in. So yeah, so the closure of this is contained in UI finite union of these UI closures, which are all compact, right? So yeah, using that you can easily prove that this is these G.
Subset of a
Yeah, that's right. Okay. Yeah.
Sir, will you see a proof of the warm-up lemma 1, or that is a homework?
That's a homework. It's sort of, yeah, it's just sort of basically this fact that, this is where we're using this, yeah, so the countable basis of open sets with compact closures. So this is, yeah, so this uses second countable. It's a consequence of second countability and the fact that, open balls have compact closures. So this is easy. It's not too difficult. You just sort of, as I kind of indicated here, maybe I wasn't very clear on this, but you can just replace all these open sets that we have with, sort of countably many open balls that still covers the space. Okay, so I mean maybe it's sort of yeah. To make it countable, perhaps you need to look at rational points of an Rn or something like that. But it's sort of this is something that you can easily do. I mean, the second countability of sort of the space is all that you really need. Okay, so okay, yeah. I mean, if you have trouble, you can always sort of ask me next time. But I think you can all do it. Right.
Sir, are we expecting any homework this weekend? Or?